Hello, everybody. My name is Frank Goldner. I'm the DOE Headquarters Program Manager for the Accident Tolerant Fuel Program. I appreciate all of you who are watching because this is a very exciting time. I just wanted to mention this year will be different than previous years, that because of limitations of funding, we are not going to have other NEOP calls at this time other than two items in the Accident Tolerant Fuel Program. These two items, as I hope you'll understand, are really very forward-looking. And that's why we thought it would be interesting to have this opportunity for the universities to get close to some items that are extremely on the forefront of what we're doing in the Accident Tolerant Fuel Program. Let's go to slide 2. Just the structure, campaign structure and mission. This is a slide that you've probably seen every year for the last, 8 years. And basically, you see the main areas: Accident Tolerant Fuel Program, advanced fuels, and also cross-cutting capabilities with a very strong tie to NEAMS. And so this time, we'll focus on accident tolerant fuels, but a very specific aspect of it. Okay, I'm going to slide 3 and 4 just show you past NEOP awards that we've done in the last 2 years. The main thing I want you to see is that they're all pretty well focused, related to accident-tolerant fuels and moving forward. And in previous years, we've had NEOPs that deal with like boiling conditions on certain accident-tolerant fuels. So we've always tried to be pretty focused. So now what is unique about these two is in the last 2 years, the Accident Tolerant Fuel Program, at the request of the utilities, working with our 3 main vendors, have wanted us to look into high burnup and high enrichment. They wanted us to move out. And, burnup up to now, as licensed, is like up to about 62,000 megawatt days per metric ton uranium. And so we already, the vendors already have pretty clear understanding with the NRC that going up to 68,000 megawatt days per metric ton is no big difficult stretch. So for the startup, when we're trying to go into commercial reactors and they start in the mid 2020s to do partial loadings, this is the burnup that they will start with, having cleared with the NRC. But the vendors have wanted to get us into high burnup and high enrichment. And by that, they mean as much as 78,000 or so in that region, megawatt base. And Goldner, of course, would like to go even higher. So that's why you're going to hear two slightly different variants of a call. I think they are very synergistic. The first one you're going to hear about is extending our understanding and our ability to predict what happens under thermal and mechanical motion of materials during transient conditions, the type that we will be testing in the treat facility. And this means anticipated operational occurrences, reactivity-induced accidents, and loss of coolant. And I'll explain later the second one, which will be more ability to predict what's going on as under normal and transient. So they're a little different, but what I'll do is I have 30 minutes reserved, so before I'm halfway over, I'll open up to Kobe Jensen, and he can either correct or answer any questions that people may raise first there. Okay, so let's go on to slide 5. So this is the first of the two proposed calls, and the thermomechanical transport under transient conditions. We're here. Thermomechanical means it's not only how energy gets out of the fuel, especially when you're in this high burnup. We don't know. There are some experiments that have been done in the world where they think the fuel may become very fragmented and be completely different looking under these under extreme conditions. This means in like up at 70,000 burnup type thing. And so, we got some data which says it's really difficult what happens, that there's particles fine or not. So in this one, assuming you're in that regime where stuff like that may be present in the fuel, how does it first interact with the cladding and the coolant from a heat transfer point of view? Is that altered? And then if there is some kind of failure, and you may have particles now directly interacting with coolant, how do we understand that? So basically that's what I'm trying to summarize, we're trying to summarize here on 5. That there will be experiments formed which will be more integral, but we need to understand it. So both of these proposals have a strong linkage with modeling, existing modeling or modeling that may be needed. And that will be a condition I will suggest. We'll strongly encourage proposers to understand the modeling situation. You know, we have a strong modeling program that interacts with us. It would be very useful for you to understand where we stand on it, because the modeling folks, some of them, like Chris Stanek, who's the National Technology Director in modeling, he's looked into this question of what happens. And by the way, the fuel we're talking about is accident-tolerant fuel, as the vendors are proposing. So it's basically UO2 with cladding that has coatings, has some kind of coated cladding, but also there's doped UO2. And that's an interesting variant that may change the nature of the fuel up in these regimes. So there's a lot to look into. Okay, the next slide, number 6. Again, this is further explaining what we mean by thermomechanical transient behavior. And again, I think the third tick summarizes it. Understanding and developing models to describe energy transfer, and in extreme cases, what happens if the fuel can directly interact. So there's a lot of freedom. Okay, and as the last tick says, we'll go to the next slide, number 7. And this is just a lot of examples of both LOCA situation and when you have dispersal, what may happen. So this is just an overview. I don't want to go into details on it, but it shows different regimes that may occur. You know, but basically the question is the fuel is different, and it's either pressing and interacting with the clad and transferring energy, maybe distorting it, or it's actually due to a burst or something like that has gotten to the coolant. So number 8 is the final slide, and again, this is really a bottom line slide. But by the way, I would strongly urge you to read the text. There's a lot more general explanation in the text that's posted, you know, for this subject. And if there are any questions, obviously the technical point of contact is Kobe Jensen at INL, and he's very involved in our plans for transient tests and stuff like that. So he's a very good one. As a matter of fact, I'm gonna cut it off now, since I have a couple of minutes, and first open up if there are questions, and if not, I'm going to then ask Kobe if he thinks I've explained it good enough or if he wishes to add. So if we can open it up to questions, if there are any.
Okay, yeah, we have a couple of questions. The first one is on FC 2.1. Would proposals that include a focus on thermal hydraulics in addition to thermal mechanics be of interest?
I'll ask Kobe to correct me, but my feeling is you can't avoid thermal mechanics if you aren't also aware of thermal hydraulics. Kobe?
I agree with that, Frank. I think that's completely in the scope. I mean, I think there's in the slides that Frank is showing here, I think we're trying to show that there's strong connectivity between these different physics, and you can't really focus on one without accounting for the other. So I think that's fully expected.
Okay, someone's asking if you could please go back to slide 6 for a minute. Perfect. Okay, next question. Will the U3 Si2 fuel type be considered as relevant for this call?
That's a good question, but I think the base fuel right now is UO2 or doped UO2. Is that your understanding also, Colby?
Yes, I agree with that. I think those have the highest priority. If other fuel types were to be considered, I would think that there would need to be a strong case as to, I guess, the value proposition. But I think from the program standpoint, the way we see it, the UO2 and dope are the primaries.
I agree. Let's assume it is the primary, because I believe now the party that was considering that has also defined for the time being UO2 and doped UO2 along with its coated cladding. So let's not recommend that at this time.
Okay, are NEAMS codes to be used in modeling and simulation proposals? If so, which ones? Which NEAMS codes?
Well, I think that's for you to recommend. We're encouraging NEAMS involvement. I don't think it has to be NEAMS codes. Colby?
Yeah, once again, I agree with that. Some of the phenomena, I mean, we're showing examples in these slides, and some of the phenomena that we're talking about here, there's opportunities that maybe don't necessarily fit into a particular NEAMS code. But if it does, I think that's what we would encourage. But there are some things that maybe don't fit really well into the capability of the current NEAMS tool set even. So those things are things to be evaluated by the proposer.
Yeah, I think we're really pushing beyond the boundaries of what is in the existing set of codes. I mean, I know some NEAMS codes are being thought of how they would deal with this, but I'm telling you, fuel fragmentation, I haven't seen that show up in one of our codes yet.
Okay, next question. You mentioned doped fuels are of interest and how they may behave differently. Should only dopants as CR and AL, as in the adopt fuel, be considered, or are other dopants also of interest for this call?
No, I think you should definitely only consider dopants that are the primary candidates, and so therefore I think it's CR2 and also the aluminum, the CR aluminum variant. I think you should use what the current vendors are in their primary. You know, we want to give this the most opportunity to get people involved in what is highly relevant. And so right now, our priority is the existing doped fuels that the vendors are now considering in their prime priorities.
Okay, are experiments required for FC 2.1? How about empirical data instead?
Yeah, I'm going to leave that to Colby. My initial reaction is they can't be required, but they certainly, I think we'd like to have recommended what is necessary to accompany what is proposed. I'll leave it to Colby on whether it's required. I'm not sure.
Yeah, I think the way that we're looking at this is that we'd like to see the connectivity between experiments and modeling, but actual experiments may not be necessary where there's data available. So if data that's available from historical experiments could be used in a new way to support some of this development, that makes a whole lot of sense. So I think it's really about making the connectivity to develop the phenomenological understanding and hopefully extending that into some kind of a model that can be incorporated into a tool.
Okay, I think that's pretty clear then, that we are interested in understanding phenomenon and how it can be or needs to be tied to modeling. Any more questions?
Yes, there's a few more here.
Wow. We're in business, Colby.
Okay. Are the proposers expected to use treat facilities And do experiments have to be done on irradiated fuels?
I don't think there's any requirement specifically for facilities and or radiated fuels. I mean, this is only 3 years, and it's very hard. So I think again, go to the last answer. You don't have to tie it to experiments, but obviously we'd want to like to know how it can be tied. If we're going to do modeling suggestions for modeling, it should be tied. So I would like to at least see what you recommend be done. And then people like Colby and others will see if that can be done. Colby?
Yeah, I agree. The budget and scope of this is not intended to support this project designing an experiment for treat. However, maybe it could lead to something like that in the long run. I think, Frank, you said it well. This last slide 8, also sort of, I guess, hones in on this discussion a little bit more. The fact that we're doing tests and treat underneath the program funding and related work, there's a lot of things that I think are easy tie-ins already for experiments that will be ongoing over the next few years on high burnup fuels. There's historical data that's out there, and potentially even, like I think aligned a little bit more with the last question, there's a potential to run some smaller separate effects experiments probably that could connect in well with some of the objectives of these integral type behaviors.
Yeah, I can't imagine that if a good response would, I think, automatically start giving ideas of what we would need, because as I said, this is a new area. We haven't explored that much in the US. There's a couple of experiments overseas, but they're not, in my opinion, very well calibrated or qualified. And that's one reason we will be doing work. So this can fit into what we plan. Okay, next.
Okay, next question. And this is the last one right now, as far as I
Good.
on my screen. If we propose experiments that utilize treat, will we need to apply for NSUF access as well?
I don't think that's required. If it makes sense, it's okay. But to me, it's what this recommends we do, not necessarily where. But so it's not required that I think that there has to be an NSUF. I think that ties into the previous answers. It may lead us to testing and things, but it's not a necessary condition.
Okay, it looks like that's all the questions we have. So thank you two gentlemen very much.
Okay, wait a minute. Colby, would you stay on showing the slides, please? And Nathan, are you on audio?
Let me see if he's here. Hang on. We are Nathan Capps. Okay, let me find him. Just a second.
I will stay on, Frank.
Yeah, I appreciate it. If only to slow the slides, but if for some reason Nathan doesn't get on, obviously we can work in the same mode, because there is a relationship, a synergism.
Okay, we do have Nathan here. He doesn't have his audio pin entered, so I can't unmute him, but I'm setting it to him now. As soon as it turns green, I can unmute him.
So Colby, if you would go to slide 10, excuse me.
I don't see that he has put it in yet. Oh, no. Still don't see.
Well, I can start while you keep working on that, okay?
Okay.
Yeah, let me start. Okay, so this second one is entitled High Burnup LWR Fuel Rod Behavior Under Normal and Transient Conditions. So the key delineating difference, in my opinion, from 2.1 is whereas 2.1 wants to extend you beyond current understanding on behavior, both thermal and mechanical behavior. This one is to improve our understanding to predict fuel rod response and behavior of this very high burnup material under normal and transient conditions. And with the idea of figuring out what's the most limiting thing, you know, before you burst, things that are driving you to limiting might be fission gas, a change in morphology, as I said, to particles and all. So this one is aimed more at considering how we understand what's happening up to these conditions, and not necessarily the energy transport from the fuel to the coolant, whether there's a failure or not. So this is more under extending current understanding, okay? And the transient conditions are, anticipated operational occurrences, reactivity, incidents, and loss of coolant. So it's the same type of stuff that drives you, but it's different. So on 10, the most operational bullet, I will say, is the second one. Okay, what is most limiting? And again, especially when you get this the new behavior of the fuel. As I said, there's a few experiments overseas that have shown that you may get a lot of fragmentation, whether it's to big chunks or whether it's fine powder. I don't think I know. And that's one reason we're going to be doing tests in the U.S., just like for FC to support where FC-2.1 may support. The same thing is here. But this is more looking with what you have now at your disposal. Again, same encouragement. Try to understand what existing modeling can do or could do, so that you're not working on your own. Understand what the vendors, what is their primary fuels. And I said it's UO2 or doped UO2, and it's coated cladding. That's their primary thing. Whether it's metal or ceramic, there's a couple of coating. There's actually 2 or so primary coatings being considered. Some with chrome type, and then there's also the concept, which is a different proprietary coating of General Electric, called, I believe, Armor. I hope I haven't gotten the wrong terminology. It's called their armor. So that will have to be understood, and obviously understanding the vendors is one thing. Okay, so that's what's on slide 10, trying to clarify. Again, on 11, applicants may, on the second, the primary goals are kind of like what I've been saying up to now, but the second major bullet on 11 says you may consider novel experiments and or modeling to inform the analysis. So the focus is different here, and that doesn't have to be. As a matter of fact, it's not aimed for necessarily a treat type environment. It may be something that can or would be done elsewhere. And again, so the second bullet is almost, to me, this task will lead to guidance and recommendations of what experiments novel can be done, not necessarily in one of our laboratory irradiation facilities. And you'll see the other 2 bullets are pretty important on there. Applicants should not consider developing new safety license. Again, we're trying to understand what's occurring, okay, but not necessarily whether it affects or not existing or future potential experiments. So have you made the connection with Nathan?
Let's see here. 1 second. No, he still hasn't entered his PIN so that I can.
Okay, then I will say, are there questions?
Yeah, there's a few questions here. You bet.
All right, we'll do our best to take them. And what we'll do is we'll let the questions go to Nathan, so we can see if he wants to modify what I and maybe with Kobe's assistance can say. Okay.
Okay. One of the first things is a comment from Madeline Feltus at HQ. She says that any UP call pays for the research at the university and any experiments or modeling done in residence at the university. If an experiment needs to be done at the lab, an NSUF grant proposal could be submitted later, and that pays only for the lab in situ tests, PIEs, etc. NSUF grants do not pay for the at-university tasks. And then she says for everyone to please see the NSUF part of the CINR FOA and talk with Rory Kennedy if you have any questions.
Yeah, I think that's a general statement of the value of NSUF if some experiments are proposed.
Right.
I appreciate that comment. Thank you, Madeline.
Okay, and a question. Can a surrogate rod be used and get irradiation from a proton accelerator versus a reactor to get an equivalent high burnup condition?
I find that an interesting question. I know that there's lots of ideas of using it. I would not personally rule it out, but obviously, again, remember, you only have a certain limited period of time because we talk about novel experiments. I think this qualifies as a novel proposal. So we'll see how Nathan reacts, but initially I would say this is not unreasonable.
Okay. Next one. Does the effort need NQA-1 quality assurance for this call?
My reaction for these two proposals, I think we're not in the ballpark yet where this might provide data that would support a licensing application at this time. So I think it's a little early to require NQA-1 at this time. Colby, do you have a comment on that?
I think you got it exactly right. I agree with what you just said. I wouldn't say that's a requirement for the data or whatever's generated in these proposals.
Because we really want to understand either phenomena or how energy is transported. So I don't think any of this is yet at that stage, but it's a reasonable question. Thank you.
Okay, next. Can the PI use a university reactor for irradiations?
Excuse me, can the PIE what?
Can the PI use a university reactor for irradiations?
My gut reaction is why not? Colby?
Yeah, I mean, I think that's an open enough question. If it fits the need, then it should be well described in the proposal.
And how it fits in to either helping to understand, what's going on or what's limiting. Sure. Thank you.
Okay, next. Can you please repeat the key difference between FC 2.1 and FC 2.2?
Okay, my interpretation is that in 2.1, we're trying to extend our understanding of what happens in the transport of both energy and or, if it occurs, material when we're in a transient. And I would say a key test is the type of thing that we think we may have to do and treat, okay, where we really want to understand not only what is happening up to a point in which the fuel might get to the coolant, but even if that occurs. Whereas in 2.2, I think we're trying to understand what's going on. Okay, as you get into this high burnup mode, in the high 70s, what's going on? under normal and transient conditions. That means it's almost more fundamental, and it's certainly related to the other one, but it's more, this is much closer to coordinating, in my opinion, with work of the NEAMS program, because obviously this understanding has to ultimately be related to what a NEAMS program capability can deal with. So this is almost more near input to what we already proved. It says, if you read again the type text, but not the slides, you'll see in the last paragraph, aimed at improving the ability to predict the fuel rod response under these transients. That does not necessarily mean where it goes to, because they're looking for what's most limiting. That's in that section also. So they're looking for what will limit you. What is going to drive you into trouble most? Is it going to be fission gas, pressure on the clad as you go into off normal, or is it going to be large particles which are digging into the clad, enhancing, So it's somewhat different. If there's still a clarity, I would say, let's keep. I would say send a definite question to Nathan. But I think that's the main difference, and Kobe. Now, I've struggled with clarifying this in my mind, so this is not the easy. I realize, but the good news is we have only two, and so I'm hoping we can get a couple of proposals in each of these, that are synergistic. Whereas last year I was lucky if I could get one for one proposal. So it's an opportunity. I don't know, Kobe, any further suggestions on clarification?
I don't think I need to say too much more. I think what you've said, I generally agree with. Obviously, when you start talking about needs for high burnup fuel, there's going to be some things that sort of are going to be overlapping. But you can see that with the similarities or commonalities, at least between the two, 2.1 and 2.2, you can see what the priority is of the program. And I think I just reiterate what you said, Frank, that on the first one, it's really a more detailed look at some of the phenomena associated with the transients themselves. And I think the second one does have a little bit more of a tie to high burnup cores and associated behaviors that are of greatest importance to considering high burnup core design and its implications. So
yeah, what's the worst on the second one? I'd like to know what's the worst thing, what's going to drive you the most to get into trouble that number one has to deal with. Okay, what's yep. driving you? What is the phenomena that's driving you? So see if that helps. And as I said, there's nothing wrong until we get into the submission process to seek further feedback from the technical proposers. I think we've run out of time. We've even gone over a couple of minutes. So
Frank, we just have one more question here. Let's go ahead and do that. We just had a break scheduled right after this. So
okay.
Do you prefer experiments to modeling, or do you like to consider both modeling and experiments? This is our last question.
I'm going to be flippant and say yes. I think ultimately experiments and modeling, they go hand in hand. Sometimes one leads the other. And I think, in my opinion, 2.1 will probably be that. It will, lead into things that modeling will have to consider. Where 2.2, I think, is already hand in hand with existing models. And again, I say relations with NEAMS are encouraged. Okay, to see what can be done in coordination. And knowledge of what the existing program is doing is obviously, and remember, this is beyond 62 or almost beyond, we said it's beyond 62, but we know that we're pretty clean with NRC up to 68. So again, it's the really next big jump where the fuel is changing, you know, due to the gradients and stresses in it that are maybe quite different for what occurs with normal fuel in design basis accidents and transients. So that's what I'm seeing. We're getting into a new area, and I think this is a wonderful opportunity for universities to start getting close to the state of the art we're pushing with this program. So again, I'll end by thanking everybody who's called in. And again, I want to make a statement. If you come in with a great proposal and we recognize it and you don't get funded, we are so limited in funding this year. It's almost a shame. But I do think we will get a couple in each of these possibly that we can do. So never assume that if you don't make it, and this is true always with NEOPS, that's not because you're not good. It's just that we've had difficulty in selecting, and we do our best. So thank you.
Okay, thank you, gentlemen. And we will take a break now, and then we'll be back at 4 p.m. Eastern Time with NEAMS and MS-NE2. And just as a quick reminder, in the handout section of this webinar, the webinar schedule is posted there that you can download, and the Workscopes are posted there, the draft Workscopes. So you can always access that anytime right there in the handout section of the webinar application. Thanks, everybody.
Thank you, Colby, and everybody else. Bye.
Bye.